And good evening, 8-bit physics students. Well, tonight we are making our jump from electricity and magnetism to fluid mechanics. Fluid mechanics is a great topic. Over 70% of the Earth is covered by water, and everything from hydraulics to pressure to lots of stuff going on with fluids. So, this is just a one chapter little unit that we're going to do. And a lot of folks kind of think, wow, after all this craziness with E&M, it's kind of nice to get back to something you can see and touch and feel and that kind of thing. So here we go. Some of this might be review. Well, I hope it's review, actually. So I'm going to go through it kind of quick. Okay, density. Physicists like to use the Greek letter rho to represent density. So instead of thinking of resistivity now, we're going to think about density, which is mass over volume. Our book and the AP test, when it talks about units for density, we use kilograms per meter cubed instead of grams per centimeter cubed. So one number you will have to memorize is the density of water. Okay, so in chemistry class, the density of water was 1 gram per centimeter cubed. But in physics class, the density of water is going to be 1,000 kilograms per cubic meter. All right. Now, if you need to, for the problems in the textbook, know the density of something else, there's a nice little chart here, table 10.1 on page 256. You can look up a whole bunch of densities, and of course they're all measured in kilograms per meter cubed. Okay, so the next thing we need to talk about is pressure. All right, Mr. Gerson, I'm taking 7-8 tests. I know all about pressure. All right, pressure though in the physics sense is force per unit area. Okay. A force being pressed upon a given area. So the formula is P equals F over A. And the SI unit of pressure is just all SI units, newtons per meter squared. And we refer to as a newton per meter squared as a Pascal, abbreviated PA. So a pressure of 1 Pascal is a pressure of 1 Newton per meter squared. Now, pascals is the unit that'll be on the AP test, but in the problems, there's some other pressure units. Sometimes we refer to 1 atmosphere of pressure as the pressure due to our atmosphere, and we just call it 1 ATM. 1 atmosphere of pressure is the equivalent of 101.3 kilopascals. That's kPa. Don't confuse that with kDWB, right? 101.3. So right now you are probably experiencing 1 atmosphere of pressure, or 101.3 kilopascals, or 760 millimeters of mercury. We use this with barometers a lot. This is the height of a column of mercury that atmospheric mercury could support, or 14.7 psi, or psi. Now, don't confuse that with the Korean rap star. This is pounds per square inch. We probably won't use this all that much. Okay, so pressure. We know a lot about pressure now. I got a question for you. Mr. Kirsten, I was at swim practice the other day, and I swam all the way to the bottom of our pool, right? And my ears started popping. Why were my ears popping? Why was there all this pressure at the bottom of the pool? Well, let's figure out how much pressure there would be at the bottom of a swimming pool. Well, the pressure down there is like any other pressure. It's a force per unit area. So let's say, the area is the area of my head here. Let's say my head looks like a square and it has some area. It would be force per unit area. Well, the force that's coming down on your head is really the weight of the water that's sitting on top of your head. Well, the weight of your water would be the mass of that water times gravity, right? Times 9, the acceleration due to gravity, 9.8, divided by the area. Well, what is the mass of this column of water that's sitting on my head? Well, it would be the density of that water times the volume of that water, right? Okay, so mass is density times volume, right? Well, what would be the volume of this column of water that's sitting on my head pushing down? Well, the volume, right, would be equal to this area. Oops, you guys can't see that. This volume of this column of water on my head would be the area down here times the height, right? So I've got a column of water here pushing down on my head. Therefore, the pressure would be rho times A times H, because that's the volume, times G divided by A. And lo and behold here, I have an expression for the pressure a fluid exerts when it's at some height h. So if you're some height h underwater, the pressure down there would be equal to the density of water times g times the height or the depth of that water. Okay? All right, well, we have almost all the preliminaries done for what we need to do here. One more equation here. Absolute pressure is equal to atmospheric pressure plus gauge pressure. Mr. Kersen, what do you mean by this? Well, here's a pressure gauge, right? I use this to check the pressures on my car that I drive to school every morning, my Ferrari. Right now, this pressure gauge is reading 0. Is that because there's no pressure on here? Well, no, it's reading 0 because the gauge pressure is 0. All right, a gauge usually, for instance, if I measure the pressure in my tires to be, I don't know, 150 kilopascals, that's the difference in pressure between the inside of the tire and the outside of the tire. To get the total absolute pressure inside the tire, I would have to add atmospheric pressure to gauge pressure. So, right now the gauge pressure is 0, right? But the absolute pressure here would just be equal to atmospheric pressure, right? Okay, let's finally get to our problem here, problem number 14, okay? And problem 14 is about a swimming pool, and the swimming pool has a length of 22 meters and a width of 8.5 meters and a height or a depth of 2 meters. And it wants to know what the pressure is, the absolute pressure is at the bottom of the pool. Okay, so that is equal to the atmospheric pressure plus the gauge pressure. Atmospheric pressure would be 101.3 kilopascals, right? Plus the gauge pressure, which would be equal to the density of this water times G times the height. So this would be 101,300 plus the density of water times 9.8 times the depth, 2.0. And we would get an absolute pressure at the bottom of the pool of 121,000, if you round to significant digits, pascals, all right, or 121 kilopascals. Okay, so that would be the absolute pressure at the bottom of the pool. And this is for part A. And the second part of part A says find the total force the total force that this water is exerting on the bottom of the pool. So I'm going to rearrange my pressure equation here. And the total force then will be equal to the pressure, which we said is 121,000 pascals, times the area, which that total area at the bottom of the pool would be the length times the width. And I would get a total force pushing along the bottom of, this turns out to be 2.3 times 10 to the 7th newtons. Okay, so that is part A. Part B says, hey, if the pressure at the bottom of the pool is 121 pascals, what's the pressure right here along the side of the pool, almost at the bottom? Well, if we're almost at the bottom, water exerts, or any fluid exerts, pressure in all directions. So the answer to part B is just the same as the answer to part A. That is, at the bottom of the pool, the pressure is 121 kilopascals, while the pressure against the side of the pool, very close to the bottom, would be 121 kilopascals also. Now, if I went up the height of the pool to about halfway up, then the pressure would be less. All right, nice job, physics students. Speaking of Psy, the Korean rock singer, he at the American, what was it, at the Grammys or American Music Awards, he did a little duet with MC Hammer, and I just wanted to show you guys that when I was your age and taking physics as a student, I was a big fan of MC Hammer. Here we go. I got MC Hammer's first album, Please Don't Hurt 'Em, with his hit Can't Touch This, along with his follow-up, Too Legit. Too Legit to Quit, or Too Legit to Quit. Hey, hey. Good stuff. All right, nice work, AP Physics students. We'll see you tomorrow.